this one definition. There are actually two definitions. So we say that our group has property Tn with these brackets if the cohomology for any unitary representation vanishes for i's up to n and every unitary g rep pi. That's a straightforward generalization. If you think of this Delorme-Guichardet theorem that we've seen yesterday in degree 1, characterization of classical property T. But in this theorem, there was also this equivalence that said, actually, we can test property T in degree 1 just by looking at unitary representations that do not contain invariant vectors. And so you could also define it by the vanishing in the same way, but just for unitary representations without invariance. And so the remark from yesterday is that this T1 in both ways is just classical T. And we will see that it's actually a difference. So in higher degree, that was a phenomenon in degree 1, that it doesn't play a role. In higher degrees, we will see there is a difference between these two. And sometimes it's actually an advantage that there is a difference. It's also something we will see. Right, so there was, this is the definition that somehow we chose in the paper with Uri. There were variations before. There was a paper of Novak and Uri Bader, which was a slightly different definition. Even earlier, there was a paper by De Chiffre, Klebsky, Lubotsky, Thom. They also had a definition. So there are slight variations that you can do in defining higher property T. This is our working definition for this course. But they're all quite similar, yet not completely identical. So as a consequence of this ultra-power technique, we get now a result that tells you we can check this condition, both of these conditions, just for the reduced cohomology. So let me formulate this. Let gamma be a group of type F infinity. So it has like a nice space on which it acts, contractible space with finite skeleton, maybe even co-compact. And then gamma has T1 if you have this vanishing for the reduced. And I'm only formulating this now for discrete groups gamma. So let's prove this. This is with what we have relatively easily now. So the thing is that if you have type F infinity, so you have this nice model space on which your group acts, we've seen that you can compute your group cohomology from a complex which is a Hilbert complex, consisting of Hilbert spaces with boundary differentials. So for that argument, I don't care that much how it looks like, but we've seen under this condition here that can be computed from a Hilbert chain complex. cochain complex. Let's just denote it by C star. And you can look at the second lecture how it looked like. Now, if you have that Hilbert chain complex, you can take its ultra power. And it's not hard to check if you look at how this complex looks like, that this ultra power actually computes the cohomology of the ultra power of the representation. Okay, so let's, how do I, yeah, let's denote it also like that. Okay, the ultra power of this representation, again, a unitary gamma representation, and it's easy to see that this complex computes this. Okay, so now let's assume that we have this vanishing for every representation with that property, and we want to show that we have this vanishing for the ordinary cohomology. So how do we do that? So let P some gamma representation now. We want to show this vanishing for the ordinary cohomology. Suppose it does not vanish in this range. Right? Suppose by contradiction it does not vanish. Then we've seen in the section 1.2, I think, the lemma in 1.2, that this would imply that the non-vanishing of that, right? Because we did a very general lemma concerning these ultra powers.
Sorry?
Yes?
Don't you also need finite abelianization in your criterion?
No.
But don't the important groups also satisfy the condition of the right?
Oh, I need not finite, I need, yeah. I need property T, classical property T. You're right, sorry. And classical property T. And I need it in the very next step. Yeah, that's a very good point. I forgot about that. Thank you. Actually, it's now that I need it. Right. So this would contradict our assumption, right? Provided we have no invariance in the ultra power. And we had this lemma, and this was in section I think this was probably 1.2, actually. This was not 1.2, this was later. But somehow in 1.2, we've seen that if you have no invariance and you have property T, then you have this by classical property T. So we can apply somehow to this ultra power representation our assumption on the vanishing of the reduced cohomology, and we get a contradiction. So the assumption leads to a contradiction. All right. And Antonio was completely right that, and this is it's very interesting, there's much to say about this. So if you have a nilpotent group, then it has this vanishing in all degrees. But for a nilpotent group, you will never have this vanishing without the reduced in all degrees. So typically, the cohomology of a nilpotent group in a unitary representation will be non-Hausdorff. And so, and that's the difference. But you need property T to conclude this. And, okay, no, I won't say more. There's a very interesting story about property T and this vanishing here, related to other rigidity questions.
The converse is obvious.
Yeah. Converse is obvious, because the reduced cohomology is a quotient of the ordinary cohomology. All right, so that's our definition of higher property T, and now let's go to the historical first manifestation of that, which is Garland's work. And it's not just Garland, as somehow what I will present is built on various elaborations and generalizations of Garland's work. So there is Ballmann-Swiatkowski, which is what I'm following mainly. Schuk, there is Dymara, Januszkiewicz, long names, and Oppenheim. So many people improved and built on this work of Garland, but the general idea is there, was done in the 70s, and it was used to prove higher property T for simple groups, simple algebraic groups over non-Archimedean local fields. Okay, so what's the general setting of this method? And people talk about the Garland method because there's a kind of general method behind it, not just a single theorem. So general setting. Let me put this a little bit above. General setting. What's the rough idea of showing vanishing? And in this setting, and for the applications of this method, it will be about the bracket Tn. So very, very rough idea in simplest terms. So here it's a situation where the group in question will act on a nice contractible simplicial complex. So the setting will involve some d-dimensional simplicial complex. It will be pure. I will say something about that. A technical condition, minor condition. And it will have a co-compact action. And you could also somehow talk about G. The G will be a totally disconnected group. They also act on these complexes. But let's take gamma here, and maybe for the discussion, let me just assume freeness for a moment to make it a little bit easier. And now, in that situation, again, as we've seen, we have this Hilbert chain complex. Let me briefly write it out. If you have a unitary representation of gamma, then we had this thing where here we have the simplicial chain complex, and we look at gamma equivariant maps like that. And if we have a free action, then this was just, as we've seen, a finite number of copies of the Hilbert space. And how many copies? Well, depending on how many cells I have in degree P here. Again, and let me say again, computes provided this complex is contractible. And reminder on the Hodge-de-Rham that if you look at the kernel of the Laplacian in degree P, then it gives us the reduced one. And somehow, what I did here, I did it for this bracket Tn, but the same argument, it's actually easier because you don't need this step. It's also true for the other bracket. So if we manage to show by this method somehow that this vanishes for all pi, we also have the vanishing for the ordinary cohomology. So somehow what we are after is understanding the Laplacian. Garland didn't use an ultra-power technique. Actually, in the work, you can circumvent this. But since I introduced it, it's just convenient to refer to that. And what is the idea? the like very, very simple idea for showing the vanishing here. Well, you show something like that, some estimate like that. Here is a constant. And this of course readily implies that if you have an element in the kernel, then this is 0, so the norm of V is 0. So the kernel is actually 0, right? Very trivially implies that the kernel, which is the reduced cohomology, is 0, and by ultra power, and yeah, you try to do this for every p, I should say, for every p. And then by ultra power method, you get also this for every p. And okay, the constant might depend on the p. Actually, it will not. Actually, it will not. So that's the very rough idea. So how do you do that? So somehow you want to control something like that. And the way you control it is by controlling it locally, by controlling Laplace operators of links, of vertices, of edges, and so on. Let me make this more explicit now.
For the first bullet point, that C is independent.
It will be, yeah. Yeah. All right. So to explain what I mean, let me first tell you what localization means. This means really trying to look at a code chain in this complex and trying to understand what it locally does. And for that, let me remind you or introduce the link of a vertex. So let's take a K simplex, and not just a vertex, a simplex. Let's take tau, and then the link of tau is, let me first formally write it down and then draw a picture, is again itself a simplicial complex. And so I will denote the length by x tau. And you can say what is the somehow J skeleton, the J simplices in this simplicial complex. And you can formally write it like that. Okay, so how should you think of this? In this notation, you should think of this J simplex sigma here as an ordered set of J plus 1 vertices. So this is somehow like something like that. It's given by its vertices. And if I write this, I just concatenate these two, right? I first write the vertices of sigma and then the vertices of tau. So all these simplices that, if I combine them with tau, give me a simplex of the corresponding dimension in X. This is the J skeleton of this link. And if you look at the following picture, so let's okay, so here you have a two-dimensional complex. Let's write like this. For example, like that. And let's say tau is here a zero simplex, so it's just a vertex, then you look at all the simplices that contain this tau, but take somehow the part that's just take the subsimplices that do not contain tau in these simplexes. So here, for example, you would take this, this, this. So this simplex would not be in the link because that 2 simplex is not there. Just the 2 simplexes that are shaded are there. So it's like you're taking the unit sphere around that point in a simplicial sense. It's like the neighborhood, the one neighborhood. This is what you do when you look at links. And if you have a chain now in our original complex, we can localize it. We can look somehow at an induced chain that only lives on this link. This is this localization. And the definition is the following. So what was my notation for the complex again? Yeah, it's Cp x pi gamma. And there is a map to challenge is always to get the degrees correctly here. So tau is now a K simplex, and you have a map like that. So you take this cochain, right? This is a cochain that assigns something to P simplices in X. And now you want a cochain, and let's call it phi tau. And phi tau, what does it do to a simplex of that dimension? Well, it just takes phi sigma tau, or tau sigma. Now I'm a bit confused. I think if I wrote this, it's probably this. So somehow it would evaluate this simplex here as what phi does to this 2 simplex. And there is somehow, when I write this, let me explicitly say what is written here, because you see there is no gamma, and that is correct. So here I really mean the simplicial chain complex of the link. The link is something finite. And there is no equivariance here. So you could also think of this thing as like the real chain complex of this link tensored with HP. HP and the action on HP, it's not there, right? There is no gamma. And that's actually an important point. So, and also one word of caution, this is not a chain map. There are relations you can write down with the differentials, and they're of course also important to study, but it's not just a chain map. Yes?
Is it P minus K minus 1 in the exponent?
It's yeah, either here or here, right? So I should do P. You're definitely right. Yeah. Yes. No, it's P. Yeah. Thanks. All right, but you can look. So again, it's not a chain map. There's still some relation. I will not write it down that are preserved, but somehow you have definitely just a homomorphism in that degree. Now, what is Garland's method in a nutshell? Garland's method, remember, we want to control this scalar product of the Laplace operator, right? And so Garland's method is the observation. I mean, it's more than just an observation. We can compute for a cochain in our original complex the norm and also this scalar product we're interested in by potentially complicated sums of various localizations. So this here is the phi tie here. So this Laplace operator is just the Laplace operator of in this finite complex. It's something we'll see in an example like the Laplace operator on this finite graph that we've seen. And somehow if you run through various taus, you can compute those things by basically a sum of those. And somehow philosophically it's maybe plausible, although the actual implementation is somehow here the difficulty. Conceptually it's not that difficult, because if you think what does the Laplace do, it's somehow the Laplace operator, the definition of Laplace operator involves somehow the neighborhood, right? The one neighborhood of, if you look at this as a vertex or at an edge, it involves somehow the neighborhood. And somehow now you're summing up in the links the Laplace operators, which also do something of the neighborhood. So you try to sum up everything. There is a lot of double counting. And you have to be very clever in finding right way to write it, to avoid double counting and so on. But somehow maybe conceptually it's not that surprising that you can somehow express these things by summing up in a very clever way all these contributions. And this is what Garland does. And again, somehow the difficulty is to actually do this. It's a lot of bookkeeping involved. And I don't want to do it here. But it's
complication just arising because this is not necessarily a chain map? Like, if it was, it would be straight.
It still you would run into complications. But in certainly to express somehow, this is very easy. This I could do. I won't do it, but this is something that's very easy. But you're right, here it's a bit more complicated. Certainly adds to the complication, but there is, I think, fair to say that it's a bit more than that. But that's the general idea. And now, let me give you a statement that is an implementation of that very general idea. And this is following, maybe I do it on left-hand side. And that's following the work of Ballmann-Swiatkowski, which is, I think, if you want to read about this method, I would personally recommend that paper. But let me still say here the title of this subsection, Garland's theorem, and they also say in their paper that they are somehow doing this. So here is a concrete statement. So our X is d-dimensional. As before, we have this group acting. And let the degree we're looking at be between 0 and d minus 1. And we want to assume that for every tau, and now we're looking at L minus 1 simplices and looking at the links of those, that the link is connected. That's actually also one of the reasons we don't go up to dimension d, because then we would get just points in the links which are not connected. We want this connectivity somehow for the argument. And the assumption on this guy here, on these guys, is expressed by saying that let me first write it. If I look at all these taus, all these L minus 1 simplices, and I'm looking at the Laplace operators in these links, and I'm actually looking at the Laplace operator in degree 0, so like the graph Laplacian. And I'm looking at the first positive eigenvalue of that Laplacian. So here is my condition, that it should be bigger than L over L plus 1. So let me write it, what this is. or maybe let me put it here. As a kind of side remark that this is, so you always have 0 as an eigenvalue, but if you look at the first positive eigenvalue of the Laplace operator in what I denoted here by, where is it? This notation. And here I'm actually taking just real coefficients. And the reason I'm taking real coefficients, although I will write down a statement about arbitrary pi, is that the Laplace operator here, because there is no group action, there is no twisting of group actions, is just the Laplace operator for the constant tensored identity on HP. So whatever spectral bound I have also for this then, because there is no group action involved. And the conclusion is that if you have this, then the reduced cohomology vanishes, and sorry, the cohomology vanishes, not the reduced, I mean both. And okay, if X is as before and a contractible space, then this will mean that the group cohomology vanishes for every pi. Okay, so this bound here will give you local bounds of these guys here. I will write it down in a second. And all these bounds assemble in the end to a bound like in the upper board. You see idea for showing kernel is 0. We want somehow an upper bound of the global Laplacian. And we will get all these bounds for the Laplacian, the graph Laplacian of these links, and they all assemble if you do the right numbers to give you in the end the vanishing of that. That's the idea of Garland.
That's the first lowest.
Say again?
First positive eigenvalue meaning the lowest positive eigenvalue.
Yeah, lowest possible. Exactly. No, maybe let me continue here. So let me say what I said orally now. It's not a proof in quotation marks. So this assumption here means that if you look at, maybe let me indicate it by tau. So this is the Laplace operator in the lowest degree of the link. And phi is a cochain in this link. Okay, so it doesn't mean that you have this for every phi, because again, there are phis in the kernel which are non-zero, namely the constant phis. But somehow for every phi that's somehow orthogonal to the constants, you get this from this bound. So this is the meaning of this. So for phi, let me just write it like this: constant functions, orthogonal complement in Z0 so you get this. And again, because this is just the Laplace operator in here is just the Laplace operator in here, tensor the identity, you actually get it also for this, for every pi, same bound. And that's somehow the beauty. So locally, this specific representation doesn't play any role anymore. Locally, it's like it's constant, trivial representation locally on the link. I'm cheating a little bit because in the applications, we don't have a free complex. And we usually have, when we look at buildings, we have a proper action. So there is still a finite stabilizer group flying around, and you still need somehow equivariance with respect to that finite stabilizer group of tau. But OK, this is a finite group. You might want to believe that this actually doesn't hurt much, and it doesn't. All right, so now this Garland method, or did I call it Garland? Yeah, Garland method means that all these norms and scalar products over tau in the L-1 simplices, and actually you only need a set of gamma representatives, they somehow add up in a complicated manner to the bound we're looking at, namely this bound here for some c that is expressed in terms of the constants here, but it will be a positive c. And again, as we said above, this is what we're after. This will show that the kernel of the Laplacian, so the harmonic cochains, will be 0. This will give us the reduced cohomology vanishing, but since, again, we do this for every representation, the ultra-power trick will give us actually the vanishing of the ordinary cohomology. Okay, so finish using the idea that I formulated up here. Okay, so this is Garland's method. And how am I doing in time? We started at 40, is that correct?
About 20 minutes plus epsilon.
I'll just continue. All right, so what's the consequence? I mean, this is a very general theorem that was in that form in Ballmann-Swiatkowski, certainly not in Garland. Actually, to be fair, everybody says this is Garland's theorem, and it is, but if you actually look at Garland, he doesn't deal with arbitrary unitary representation. He deals with the trivial representation. And it's just when you read it, it's clear, and it was somehow realized that by the fact that we're looking locally at links and the group action doesn't play a role, that his argument also allows for arbitrary representations. But if you really look for the statement, you will find constant coefficients in Garland's paper. But the proof readily generalizes, and again, in many works of other people, this was generalized, elaborated, improved. But somehow the group theoretic consequence that, oh, my numbering scheme should be 2.2. So consequence of this theorem. So apply the theorem to acting to SLNQP, acting on its Euclidean building, Quartet's building, which is n-1 dimensional. Again, this means that we can also get the vanishing up to n-2. And then the theorem, this is contractible, Cat zero space actually. And somehow if you apply this theorem, what you have to now do is understand what's happening locally in this building. You have to understand the graph Laplacians of the links. And you can do that and conclude that this, I should write either SLNQP and also every lattice has this property. So I formulated everything here for discrete groups. But actually, in this setting, the SLNQP itself acts, and you can also right away work with the G itself. It doesn't really play a role in this setting. Going from lattice to G and back is really basically the same. So you get this statement by analyzing the links, which is non-trivial. But you can do that, and more generally, if G is a simple K group, K is an Archimedean local field, and gamma is a lattice, then G and gamma have this property, higher property T, but now D is the rank. Okay, so there is more general statement. I'm mostly keeping it to SLN all the time, but there's a more general statement like that. Okay, and also to be fair, you should also credit not just Garland, but also Kasselmann, because there is actually, for some groups, if you look at the links, they don't quite satisfy that for every non-Archimedean field, so I have a bit more careful, but in general, mostly Garland. All right, so now the last thing I want to do today is to give you 20 minutes, right? Yeah.
If you're claiming your whole hour, absolutely.
Yeah.
You have every right to.
All right, all right. No, I mean, I think 20 minutes will be just fine, but if it's 5 minutes, then I would run into a problem now. So I said, trust me that you can do this link computation for these examples. And now I want to give you an idea how to do the link computation. And I want to do it in the simplest possible case. So the example I want to look at now in the remaining time is SL3 QP acting on its two-dimensional Brouwer-Titz building. So that's my G, that's my gamma is some lattice. And we want to check the link condition. In the link condition in this example, there is no higher property T, strictly speaking. In that example, the link computation that will do it, but it will prove us classical property T. We have to go to SL4 to get T2. With SL3, we only get T1. And we want to try to understand the link now. And of course, the complications are a bit higher when you go to these more general cases, but that's somehow the simplest case. And it will also give us then somewhat a proof of the first classical property T group. We haven't seen a proof so far that we have a property T group. Okay, so the computation involves some knowledge of buildings, which I will not recall now, just not enough time. My feeling is, like in that audience, there are many people who know much more about buildings than I do, and maybe know more about buildings than about cohomology. And so I leave this, maybe if you don't fully understand the picture of the building here, to exercise session and just ask people. There are many around who know a lot about buildings. So I will just tell you that in that building, we're looking now, we want to control H1. And if you look at this theorem, we have to look at two-dimensional, so we're interested in L1. So we have to look at links of vertices. And the link of a vertex in a two-dimensional space will be just a graph, will be something one-dimensional. And somehow the link of a vertex in that building is just the spherical building of SO3 of the residue field. So link of a vertex is the spherical building SL3 P, and it's something very concrete. It's actually the incidence graph of the projective plane over FP. So the vertex in that, or the vertices, correspond to one-dimensional or two-dimensional subspaces in FP3. In this three-dimensional vector space, and so you have two types of vertices, and the edges are just if these subspaces are nested in each other. I mean, are contained somehow in each other.
Sorry, SPH, what did it mean again? What did SPH mean again?
SPH?
Spherical.
Oh, SPH, circle, yeah. Okay, so you have, let me just write this down. So you have 2M vertices where M, so there are some implicit exercises here that you might know from linear algebra. You have that many vertices, and the Laplacian in degree 0, maybe I should write the link Laplacian. If I write it as a matrix, remember we had a formula for the graph Laplacian. And it's almost the same, and why it is not exactly the same, I will tell you in a second. Right, we had this formula, but somehow it was a slightly different, the degree was here, so it was up to a scalar, the formula, but it's not exactly the formula. And that's because there is something I didn't tell you in this work. So somehow, when you write this down, this complicated bookkeeping of adding everything, it's very convenient, and that's somehow the trick to give somewhat the right normalizations in, now it's gone, but in these Hilbert chain complexes that you have. You remember this Hilbert chain complex that computes this was a sum of the representation. And somehow when they actually implement this Garland's method, you somehow weight the scalar products here. It's not just the sum of the scalar products, you give certain weights depending on the degree in which you're in, and it's somehow very important to get somehow this double counting in this process right. And so somehow this lambda here, this specific constant, is with respect to the right normalization, which I didn't tell you, but let me just tell you that this is the graph Laplacian then. So it's the same that we had, but it's slightly different scalar. Okay, so so this would be p plus 1 in this case, the degree. So let me write it down. So we have now I have to concentrate. So let's call this matrix M. And what is it? This is the adjacency matrix. So I view this as a projective plane. So the one-dimensional, I mean, I have lines and I have planes somehow. And I number them. I number the vertices. right? First the one-dimensional spaces, then the two-dimensional spaces. And somehow, because there is a duality here, the adjacency matrix has this form, and somehow the upper part is just indicates whether the ith line lies in the jth plane. All right. Now, if you compute this, and now I do a computation. And this is for I not equal to j. And why is this true for this matrix A, this part of the adjacency matrix? Well, because any two distinct lines lie in a unique plane. And if you do this for the diagonal entries, this will just turn out to be this one, since we're only 0 and 1s. This is just p plus 1, because any line lies in p plus 1 planes. So in some sense, the properties of projective plane give you somehow immediately matrix relations here that you use. And now it's just a way of cleverly writing out this, because what we're after, again, is understanding the eigenvalues of that. And somehow you have to set it up cleverly. So these two relations, let me summarize them by saying what this matrix is. So remember, M is a 2M matrix. 2M by 2M. A is an M by M matrix, where M was this constant there, p squared plus p plus 1. And now these two relations collect to the following relations, where Jm is just a matrix that only contains ones everywhere. Right, then you get on the diagonal, you get the p plus 1s if you add this up. All right, so in very similar thing, there is always a kind of duality here. You get also that this satisfies the same. So there's no difference here. And what this means for M itself is that if you square M, then you get these guys on the diagonals. So you get these matrices, and the matrix you end up with is P times the identity matrix plus a matrix that has these as diagonal entries. So you're here. All right. Okay. So I would say up to here it's kind of straightforward using the geometric situations. Now it's really like cleverly setting this up to get at the eigenvalue, which if you don't do it in the right way, you probably end up in a mess. But what you get now, the clever way to set this up is to look at the following expression. So I'm computing this product of matrices here. Let me write it what we get. If we look at this, the way M was defined, we just get, let me write it and I hope it's correct. Yeah, since M squared is this, then we subtract this, so we get this. And then for the other part, the identity matrix does not quite cancel, but we get this term. I think I want to take the square here. Yeah, that's right. Right, so for this does not completely cancel. We get this expression p minus p plus 1 squared. But p minus p plus 1 squared is just this, is just minus m. It's just this m here, if you compute it. So, what do we get now? And
did you intend for p minus 1 squared instead of p plus 1 squared?
Say again?
Did you intend for p minus 1 squared instead of p plus 1 squared?
you mean here or here? I thought it's correct. I think it's correct, right? Yeah. All right, so what do we get? Let me rewrite it. If we multiply this out, we get, we're almost done with this matrix. So there is this part which is a bit, so you get this, but this is the matrix that only contains 1. So if you take it square, you get m's. And then magically, well, magically, you get 0 here. Okay. You get this relation. Okay, that's the part that somehow it's maybe, why would you set it up like that? Okay, have to try. But what you get now is, and that's the important thing, M satisfies the following polynomial equation. Just check the time. Yeah, I think we're almost done. Namely, it satisfies this equation. Right? This is the one that we just computed for M.
So you mean M squared? So it's M squared minus P. There. The last line of the first black box. M squared and M squared. Yeah. Because you say M squared is equal to P plus JJ.
Oh, yes. It's both, right? I worked with the square. Yeah, you're right. All right. So this means, so now let me finish the chart. The eigenvalues of M are then eigenvalues or zeros of this polynomial. So we get these eigenvalues. That means that the eigenvalues of p plus 1 times the link Laplacian, right, which is here, it's just shifted. So we get 0 shifted by p plus 1. So we get this. And now, fortunately, no space here. And finally, the eigenvalue of what we're really after, the link, the graph Laplacian of the link of a vertex, will be then, so you have to divide by p plus 1, so we get this. And I already write it in an ordered way. So we're interested in the smallest positive eigenvalues. We are interested in that eigenvalue. But that turns out to be greater. What should it be? We're looking at dimension d equals 2. We're interested in the first cohomology. So L is 1. And therefore, the bound that we're after is that the eigenvalue should be bigger or greater or equal to 1/2. And this is the case for every p, even for p equals 2. It gets better if p gets bigger. And by the way, that's when I wrote Garland's theorem, probably, I'm not sure it's probably there, I said Kasselmann as another name. So the thing is that for some groups, the link computation runs into problems for p equals 2 or 3. So or higher. So for low p, some groups you run into a problem. You have to work somehow a bit differently. But for SLN, it really works even for p equals 2, and it always gives you the right estimate. So the consequence that we get, that gamma and G, which is in our case SL3QP, have this vanishing of the first cohomology, and by Delorme-Guichardet they have classical property T. Right? And you see, basically the geometry is used in these two steps, and of course in just understanding what the link is. And it gets a bit more complicated. So if you want the first higher property T result, so T2, you should look at the building of SL4QP. And you should look at the links of edges in that building and try to understand. And what you will see that there are two types of links, and one is basically this one. So we already did somehow the computation, but there's also another type. And one of the exercises is to somehow connect with the experts here in buildings and try to think how these links look like. But you can compute everything. Everything is very computable, and so we get, in the end, somehow this result, which is hopefully here. No, it's gone. This one here, about the higher property T for these non-Archimedean groups, and tomorrow I want to then turn our focus to Lie groups, to semi-simple Lie groups, and how to prove property T and higher property T there. Okay, thank you.
Questions?
Is there a notion of higher property tau, and are there groups that satisfy other than the higher property? Irreducible lattices and products of SL2.
So there is something about, you can prove something about there, about higher property tau for congruent subgroups. The higher property T, we will see, well, I'm not sure we'll see tomorrow. I will restrict to the simple case. So somehow you have to formulate the higher property T results for semi-simple groups. You have to formulate it a little bit differently. It's not exactly the thing that I wrote for this, but there is something I'm happy to share more details. But in general, I should say, like our supply of higher property T groups is very, very much limited. Somehow, I mean that is one source of examples, and coming from buildings eventually, and now like lattices in simple Lie groups. But yeah, there is not much, if anything, beyond that so far. Yeah.
More questions?
Use one.
Okay, could I or? Okay, so I have a similar question that is there. I know that the property T is kind of you can use it to construct the expander graph, but I also know there's kind of definition of the higher expander.
Right.
So can you use the kind of higher property?
Yeah, that's a very good question. So you can do something, but somehow the problem when you construct well, first of all, there is a whole slew of definitions of expanders and higher expanders.
Yeah,
so there is something called co-boundary expanders, and they have something that's formulated in cohomology with F2 coefficients. So they work over a finite field. And the reason they work over a finite field, I mean, one of the reasons, I mean, there are applications in computer science that somehow it's very natural, but also topological, there's this Gromov's topological overlapping theorem, just for those who've heard that. And it really needs finite coefficients. You cannot do it with set coefficients. You get something for set coefficients as well, but not exactly that. And then there's still a problem somehow, because somehow everything you do here is over the reals. Right, all these estimates, and somehow for this, at least consequences that expanders have, you would at least to be able to work over the integers and express some expansion property like that over the integral chain complex. And there is something you can do in degree 2 that I did with Uri, which maybe now for this question leads a bit too far. Can explain maybe more in private. But the problem is really to get this co-boundary expansion in the definition of higher expanders. You normally want it not over the reals. You want it over a finite field, or at least over the integers. And somehow to get from the reals over the integers is a bit problematic. So you get some result about two-dimensional expanders from that method, which is not exactly the definition of two-dimensional expanders that maybe you're thinking of with co-boundary expanders.
No, I'm actually thinking about the spectral definition, like the spectral for the Laplacian. So I think it's.
Oh, okay. If you think that, then it's defined in terms of the real chain complex. Yeah, okay.
Yeah, but what if it's? I also know the co-boundary or co-cyclist Garland, co-cyclist take or I don't know how to pronounce it. So what?
Systolic.
Yeah, systolic, but yeah, I'm also interested. Could you speak more about the why degree 2 is? I mean, maybe. Oh, okay,
yeah.
It was exercises. But you have another question?
Yeah, I was just wondering if the theorem is sharp in the sense.
It's sharp. Yeah.
Can you
Yeah.
give me a
I mean, there is this Steinberg representation that if you want to look at Dimar Januszkiewicz, I think it's very nicely presented. So it's sharp in degree. So in the rank, you have a representation that gives you non-vanishing. Yeah.
Okay, only if it's fast.
Is there a simple thing to look at in order to know that a group cannot have its property T n for some n? Just like looking at the abelianization could tell you whether you have property T.
Yeah. Well, if you know something about the not such an easy criteria. I mean, of course, if you know something about but everything that you need to know is something involving cohomology. So that's probably not what you're looking after, right? You're looking after I don't know, something more directly group theoretic, right? Not so clear. Yeah.
All right. Let's thank Roman again.